In stats, we wrapped up the beginning of Chapter 2 notes. We looked at standardized scores and these different test scores from Mr. Pryor's stats class. So first off, a standardized score is often called a z-score, and it is the number of standard deviations a value is from the mean. So what that means is we're going to use the letter Z to symbolize a standardized score, and we're going to go observation, like the value in question, minus the mean over standard deviation. And for now, this formula looks like this. We're going to change this formula over time, like it constantly evolves as we learn more statistics. But this is the most basic form of a z-score. So you get x bar, you get s, and for a question like you see below for Katie, we'll take 93 minus the mean, and then we'll divide by s. So let's do that. In your calculator, enter all the data and run one var stats, and you should get a mean of 80 and a standard deviation of 6.0691. So if we want the standardized score for Katie, we're going to go 93 minus the mean divided by the standard deviation. And when we do that, we get 2.142. So we would interpret this as Katie had a test score .142 standard deviations above the mean. That word above is key, and so is context. So make sure you say above or below, but yet, as you'll see on this next one for Norman, you want to be careful when you say below because it's probably a negative standard or negative z-score. So let's practice that. Z equals 72 minus 80 over 6.0691. And when you do that, you get a negative. So be careful when you interpret it. You don't want to use a double negative. So let's give it a shot. Norman had a test score. I ignore there's two ways to do this. I ignore the negative and I write 1.3182 standard deviations below the mean. I feel like that's the best way to say it. You have an argument if you throw the negative in front of the 1 and you say test score negative 1.3182 standard deviations away from the mean, because then that negative is implied. Whereas up above, I feel like it's really important to say above no matter what if you have a positive z-score. All right? Lastly, on this handout, I had some little principles of if I transform my data set somehow, maybe if, we're talking about test scores, maybe I curve the test. So if I add, for example, a 5 to every single score, that's going to increase the mean by 5. So this is adding or subtracting. So for example, if we add 5 to every observation, the mean will increase by 5, but the standard deviation will not change. So remember, standard deviation is the distance values are from each other. And if I add 5 to every observation, that distance isn't changing. They're still the same spread, but the mean is on average higher. So another example, if we multiply every observation by 5, then the mean, let's rewrite that again, is also multiplied by 5, and so is the standard deviation. That one's a really nice principle because the mean and the standard deviation would be then multiplied by 5. It's that adding and subtracting that catch people off guard because the standard deviation is not affected by adding and subtracting. All right, that was it for the opening set of notes. Next, we looked at properties of the normal curve, of the bell curve. So some things that we wrote down in class are that it's symmetric. Now, actually, let me show you what your handout looks like. Your handout starts with this right here, these Iowa test scores that are bell-shaped. And at the bottom of this page, we wrote a few just brainstorming ideas about what a bell curve looks like. So many people said symmetric. They said the mean is approximately equal to the median. One peak in the middle. Another descriptor I've seen used on a multiple choice question is it is mound shaped. It is bell shaped. Which looks like this. I think that's about it. So those are the basic principles you need to memorize. When we look at that problem I showed you, these Iowa test scores, these test scores, they follow this density curve. So the density curve, I can't quite get it all. Okay, that's all right. That's the red line you see in the graph. So the density curve is the line that can be sketched above the graph. And it has two properties. It's always above the horizontal axis. And if I was to shade the entire distribution, that means that I shaded 100% of it. That's what that area equal to 1 means. So let me write this little if here. if we shade the entire distribution, the entire graph, then we have shaded 100% of the density curve. So, for example, if I shade every single bit of this distribution under that red curving line, that all that area equals 1 principal means is that I shaded 100%. Think of it as if I throw a dart at somewhere under that red line, that red curving line, it is 100% probability that I'm going to hit somewhere under that red line. I hope that makes sense. That's what the area refers to as probability. So if we look at this problem, it's a histogram of 947 7th grade students in Indiana that for some odd reason took an Iowa test. I think it's because this ITBS test, Iowa test scores, is a commonly used test across different states. And they follow a bell curve. So this curve is called a density curve. We're talking about continuous data, and you can draw the smooth curve over the distribution, distinguishing the median and mean of a density curve. In the space you have on your paper, you wrote some about bell curves, but I also intended us to talk about this right here. So we've already talked about this and how the mean and median are different depending on the shape. So if we have a positive skew, I know this would let me change colors. I know this would symbolize the median because that positive skew is pulling the mean higher. And the opposite is true on a left skewed distribution. This would be the median. And that left skew is pulling the mean down. On a symmetric graph, this one is similar to the Iowa test score data. The mean is approximately equal to the median. And then for this weird box-shaped distribution, it is also symmetric. So I know the mean is approximately equal to the median. So that was just the purpose of that question on the front page, was to start distinguishing what makes something a bell curve and what it does to the mean and median of the data. All right? That was all that front page was for. More just brainstorming and to look at an example of a bell curve. And here, we'll end with this. We identify the three main aspects of a normal curve. It is symmetric. With a single peak. In the middle. And lastly, you can say bell-shaped or mound-shaped. All right. And distributions like that are actually called normal distributions, because that's a really typical distribution for data. All right, we'll talk more about it tomorrow. Bye.